welcome back. So, in the last lecture I introduced the concept of value at risk, and let us go back and recap a bit. Given a portfolio W for which we are to compute the value at risk and a certain probability which we call the confidence level and a time horizon, these are the three inputs that go into the value at risk. Value at risk attempts to answer the question, I am p% certain, where p is the confidence level, I am p% certain that the loss on my portfolio W, shall not exceed that number, what we call the value at risk, let us call it D, over a period of t days, which is the time horizon. So, basically we are trying to answer this question, I am p% certain that my portfolio W will not suffer a loss which is greater than the value at risk over a period of t days, subject to this probability p that we call the confidence level. In other words, you can also interpret it as the loss level which could be exceeded with a probability of 1 minus p. You could also interpret it as given a set of say 100 observations or given a set of 100 days data, it would only be in 1 minus p occasions that the loss on the portfolio would exceed the value at risk, right. So, if the underlying distribution is normal, then this whole area represents my confidence level, this entire area represents my confidence level, and given this confidence level which is predetermined, which I have to choose, which is an input to the model, I work out the value at risk at the maximum loss or the maximum expected loss subject to this probability. So, given this probability, my maximum expected loss is going to be this value of the loss or the change in price. Loss is basically the change in price over the time horizon, whatever we are talking about. So, this particular quantity here will represent the value at risk loss at this confidence level, which is the probability covered by the unshaded area, and this shaded area will obviously be 1 minus p. Now, there is another fallout of this, immediate fallout of this, that if the confidence level increases, what does it mean? It means that this area will increase. Earlier the confidence level was 95%. So, this unshaded area was 95%. Now, if the confidence level has you have changed the confidence level to 99%, let us say, then this area should be 99%. This will push this particular point more to the left, because the right hand side area should now be 99% instead of 95% of the entire area. And therefore, in other words, what will happen is the value at risk will increase in absolute terms, and value at risk is obviously a negative quantity, and it has to be it is usually represented as the absolute value of the negative quantity. So, value at risk in terms of magnitude will increase given an increase in the confidence level. Now, we come to the calculation of value at risk. Now, calculation of value at risk can be done in two fundamental ways. Either we can use a historical approach or an empirical approach, or we can work out the value at risk assuming a certain distribution, a model for the price of the portfolio or price of the asset for which we are to determine the value at risk. We will talk about both of them. Let us start with the historical approach. Let us say these are the assumptions that go into the historical approach. The portfolio under consideration does not change over the forecast horizon. And please note, when we compute value at risk, the forecast horizon is usually very small. We initially calculate the value at risk over a period of 1 day, and if required, we extrapolate it over t days by using the square root rule. The historical data used contains information useful for forecasting the loss distribution, that is it is symptomatic of what is likely to occur in the future. And the third is that the historical data follows a specific distribution. These are the assumptions that go into the computation of value at risk by the empirical method. Now, let us go to the technicalities. Let us assume for simplicity that I have a portfolio and that portfolio is a function of a certain index. For simplicity, let us assume, for concreteness, let us assume that that particular index is the BSE Sensex, S&P BSE Sensex. In other words, the value of my portfolio is in some way related to, some functional dependence on the S&P BSE Sensex. It is a one index this thing relationship, and my portfolio value is captured by value of the Sensex. So, let us again, for the sake of concreteness, work out a 1 day 99% value at risk for this particular portfolio, and for this purpose let us assume that we have collected 501 units of data, 501 units of data going back in time. Say today is t equal to 0, from t equal to 0 to t equal to minus 500. Minus 500 means we are going back in time, we are collecting historical data. So, data for today, yesterday, day before yesterday, and so on, we continue up to 500 days going backwards. So, the earliest data will be for t equal to minus 500, and the latest data that we have is for t equal to 0. There will be 500 units of data in respect of values of the Sensex. That is what is the input to the model. Now, what we do is, in this particular case, what we do is, the first step is that we construct scenarios, or we create scenarios. You see, we know the Sensex value as of today. So, let us call today as t equal to 0. So, we know the Sensex value at t equal to 0. What we are worried about, what we want to work out is to work out the Sensex value at t equal to 1, that is tomorrow, and once we know, or once we project the Sensex value at t equal to 1, we are able to capture, or we are able to determine the value of our portfolio corresponding to the projected value of the Sensex, and therefore, we are able to calculate the change in value of our portfolio corresponding to that projected value of the Sensex, and therefore, we are able to, because we will have a number of such values of the Sensex, number of such projections, how we will come back to, but we will have a number of such projections, and therefore, we will be able to define a distribution of the changes in value of our portfolio between t equal to 1, that is tomorrow, and today, which will ultimately enable us to determine the value at risk. That is the underlying mechanism that is to be followed. So, let us now start with this. So, we have got 500 days data. The first step is, I have a blank slide here. So, what we start with is 500 days data. Let us say today is t equal to 0, tomorrow is t equal to 1, and this is 500 days data, 501 days data. This is t equal to minus 500, and I have data Sensex values, data is Sensex values. I have Sensex values from t equal to minus 500 to t equal to 0. And let us call those Sensex values, let us give them a name, let us call them m minus 500, m minus 499, and so on, and here it will be m 0. Right. So, what we do now is, in order to project the value of the Sensex at m 1, at t equal to 1, you can call it m 1, or you can call it scenario 1, this is also equal to scenario 1. In order to project the value at t equal to 1, the first scenario that we will work out is by assuming that the change in value between today and tomorrow, the percentage change in value between today and tomorrow, that is, this is scenario 1, let us call it m 1 upon m 0, the percentage change in value between today and tomorrow, that is m 1 upon m 0, is equal to the percentage change in value between the last observation that we have, that is m minus 500, and the next earlier observation, which is m minus 499. So, we want that this change in value should be equal to m minus 499 divided by m minus 500. This will give me the first scenario. The first scenario value of M 1, or in other words scenario 1 for M 1 will be equal to M 0 into M 4 minus 499 divided by M minus 500. So, this is the way I will get the first scenario. Now, what about the second scenario? The second scenario I will obtain similarly. What is the second scenario? The second possible value that I feel would be of the Sensex tomorrow, given whatever information I have about the data, that is the history of the Sensex. So, S 2 will be equal to, now in this case what I assume is that the change in value, percentage change in value between tomorrow and today, M 1 upon M 0 is equal to the percentage change in value between M minus 498 divided by M minus 499, and this way we will work out. This is the second scenario, the second possible value of the Sensex that I perceive to be viable at tomorrow. And similarly, I will work out the third scenario, fourth scenario, fifth scenario, and so on. Right. So, we worked out scenario 1, scenario 2 and the various scenarios by using the chain of values that we had collected for the 500 days of Sensex, and we arrive at 500 possible scenarios for the projected values of Sensex as of tomorrow, given the value that we have as of today. As you can see, the first Sensex projection, or the first value of the scenario for Sensex as of tomorrow is given by M 0 into M minus 499 upon 400, and similarly the second scenario is given by M 0 into minus 498 upon minus 499, and similarly for the rest. So, we will have 500 possible Sensex values, possible Sensex values for tomorrow, based on the chain of data, the historical chain of data, 501 observations of the historical data that we have inputted into this particular model. Now, what we do is, for each scenario, knowing the functional dependence of our portfolio on the Sensex value, for each scenario we work out the value of the portfolio. V 1 is equal to f of S 1, S 1 is scenario 1 of the Sensex, V 2 function of S 2 Sensex, and they say for example, if you have the CAPM model based functional relationship in your portfolio, you can use this expression which is here, and otherwise of course, whatever that functional relationship is, the bottom line is that we have to work out the value of the portfolio corresponding to each value of the Sensex. Right. So, now we have 500 possible values of our portfolio. We have translated the 500 possible values of the Sensex that we projected for tomorrow into 500 possible values of our portfolio for tomorrow. Knowing each of these 500 values, we work out the changes in value of our portfolio, between today and tomorrow. We know the value of our portfolio today. We have now worked out various scenarios for the value of our portfolio tomorrow, and therefore, we can work out the change in value corresponding to each scenario. What we do now is, we plot a probability distribution, or we plot a histogram, howsoever what we work out, but we work out the fifth, because we are talking about 99% value at risk, and we are talking about 500 units of data. So, what we will be looking at, if we arrange the changes in value in descending order, the maximum positive change in value at the top and the maximum negative change in value at the bottom. Negative change in value represents a loss, a positive change in value represents a profit. So, if we arrange the data, arrange the changes in value of our portfolio as given in our scenarios in descending order, the fifth worst possible loss, the 99th percentile, will give us the 99% value at risk for one day. If you want to extrapolate it over t days, you multiply by root t. So, it is as simple as this if you want to use historical data for the computation of value at risk. This is an example that we have collected sample hypothetical values. These are hypothetical values for various days of the Sensex, and based on that we worked out these scenarios. First scenario, the Sensex value comes out to be this, second scenario Sensex value comes out to be this. The working is shown in this slide. Value at Sensex on September 20, which is this is my t equal to 0. This is my t equal to 0, 1 1 0 2 2, this is my t equal to 0, and this is August 7 2016 is t equal to minus 500, August 8 is t is equal to minus 499, please note this. So, knowing these two values, the percentage between them will be equal to the percentage between today change between today and tomorrow, and thereby we get this value, for the change in for the Sensex for t equal to 1, that is tomorrow. And similarly, the various other scenarios are worked out for Sensex, and then we work out the portfolio value corresponding to each scenario, and we work out the value at risk. Now, what happens? What happens if the functional dependence of our portfolio is not confined to a single index? For example, our portfolio may not be simply mimicking the S&P BSE Sensex, but there may be some content of foreign investment in our portfolio, there may be some content of maybe foreign currency in our portfolio, and therefore, there would be different indices which would be trailed by, or which would be reflected, or which would be mimicked by different constituents of our portfolio. Let us assume that our portfolio W is given by this expression, a weighted combination of the functional dependence of different indices M1, M2, M3. These are different indices. BSE Sensex may be the New York stock index, and maybe the Financial Times index of the UK, and so on, maybe the Nikkei index of Japan, and so on. So, suppose it is a heterogeneous portfolio, but we can identify the components, or even if it is not there, there is some functional relationship between the various components and the indices of the portfolio. The basic thing is that we must be able to determine the value of the portfolio given these various indices. Suppose I know the values of certain indices, I must be able to ascertain the value of the portfolio. Once if that is available, if that information is available, if that functional relationship is available, then we can simply extrapolate what we did for the single index portfolio to a many index portfolio by repeating the exercise, extrapolating the exercise which we did for the single index portfolio. We collect data for a sufficient number of historical days, a sufficient number of days in the past, but on the basis of which we work out scenarios for each of these indices, and for each scenario for each of these indices, we work out the portfolio value, because we know the functional relationship. So, we will have the portfolio value corresponding to each of these scenarios, and knowing the portfolio value for each of these scenarios, we are then able to fit a probability distribution, or we are able to arrange the changes in portfolio values, that is today's value vis-a-vis tomorrow's value minus today's values, rather tomorrow's portfolio value in each scenario minus today's portfolio value. We arrange them in descending order, and we take the appropriate percentile of that series to arrive at the value at risk. So, it is simply an extrapolation of what we did for the single variable, where but we need data for each of those variables, of course. The rest of the exercise is absolutely parallel. So, that done, we now move to calculation of value at risk using models. Let us start with the simplest case, single asset case. Now, for the single asset case, it is very common, it is very the common practice to use the Black-Scholes model, and because we are talking about one day in general, we determine the value at risk for one day and then extrapolate. The infinitesimal Black-Scholes model is good enough. So, we use this model ds is equal to mu s dt plus sigma s dw, and dw can be written as z under root dt. We have talked about it in lot of detail when we discussed Brownian motion. So, ds is equal to mu into s dt plus sigma into s z under root dt. If we are talking about one day, and if all these parameters are for one day, we can take dt equal to 1, and therefore, our expression simply or model simplifies to ds, the change in value over one day, change in value of our stock or of our asset over one day is equal to mu per day into s, dt is 1 plus sigma per day into s into z. Obviously, the expected value of the change. Now, what is ds? ds is tomorrow's stock price minus today's stock price, S1 minus S0. So, E of ds per day is equal to mu into S day, mu day into S plus standard deviation day per day, that is given by sigma day into S. Now, it is conventional, it is not really conventional really, but it is an approximation, but an approximation which is usually employed and which is to some extent justified. The assumption is, you see, the point is, if you look at this the Black-Scholes model, you will clearly see that the expected return scales as t. Expected return over a time dt is given by mu dt. So, expected return scales as t. However, if you look at the standard deviation scales as root dt. I repeat, the expected return scales as t or dt for that matter, and the standard deviation scales as root dt or root t, whatever the case may be. Now, the important thing is, if that is so, when we convert the annual return and the annual volatility into a daily volatility or a daily return, we divide by the number of days in the year or the number of trading days in the year. As far as the return goes, and when we work out the volatility per day, we divide this by the square root of the number of days or the number of trading days. The result you can see is, let me give you an example. And the result is, suppose 20% is the annual return and 20% is the annual volatility, and we are supposed to work out the daily return and the daily volatility, then 20% per annum corresponds to a daily return of 0.08% and 20% per annum corresponds to a daily volatility of 1.26%. Look at the gigantic difference between the two. The return per day corresponding to the same annual return is 0.08%, and the standard deviation of the volatility per day is 1.26%. So, the gap is gigantic. That being the case, it is fair enough that we ignore the first term here and we retain the second term, and we write that ds per day is equal to sigma per day into s into z, and we ignore the first term, the mu term, we ignore that, because mu per day is going to be pretty small. That being the case, in other words, what we are simply saying is that the expected change in price on a daily basis, on a per day basis is negligible, but the standard deviation of the change in price is given by mu per day into s, because the standard deviation of z is 1. In other words, what we can extend this and say that ds per day is normally distributed with a mean of 0, because we are assuming that mu per day is 0 or close to 0. So, ds per day is normally distributed with a mean of 0 and a variance of sigma day into s. whole square, sigma day into S whole square. Now, let us go to the modalities of value at risk. This was the basic model. Now, given a confidence level P, now this is the confidence level P, this is the probability P. Given a confidence level P, we define value at risk as the least. I have put least in inverted commas because please note value at risk is the maximum loss. Maximum loss is tantamount to minimum profit. You see, normally we work out the change in price by tomorrow's price minus today's price, price at t minus price at 0. Change in price is determined in this manner. Therefore, if tomorrow's price is more than today's price, you make a profit, and if tomorrow's price is less than today's price, you make a loss. So, when we are talking, in other words, if ds is positive, you are making a profit, if ds is negative, you are making a loss. So, because we are talking about the maximum loss, it would be the least value of ds, because we are maximum loss amounts to minimum profit or minimum change in this expression. The you see negative included, it amounts to the minimum change in ds or change in price. Therefore, we can define value at risk at that least value of ds, such that the probability of ds being greater than that, ds being greater is good, that is profit, or at least the lesser loss. So, ds per day should be greater than that minimum change, which is the maximum loss. This is the minimum change, this is also the maximum loss. ds star is the minimum change, it is also the maximum loss, and this is my value at risk, such that the probability is equal to p. This whole area, unshaded area, is equal to p. I repeat, why we are using least? Because we are talking about maximum loss, and maximum loss is nothing but minus of profit, and we want the profit to be least. We are talking about a profit distribution, we are talking about a gain distribution, we are talking about S1 minus S0, we are not talking about S0 minus S1, we are not talking about S0 minus S1, we are talking about S1 minus S0, and therefore, positive will ds will mean profit, negative ds will mean loss, and therefore, we want negative as much as possible subject to this probability, and we are happy with the negative being less than this quantity, which is what it is representing, right. Negative being greater than this quantity, this portion we are happy with, we do not want this portion. So, but ds per day is normally distributed, as we did in the previous slide, normally distributed with a mean of 0 and a standard deviation of sigma per day into S. Therefore, if z is the standard normal variate, because the mean is 0, we have z is equal to ds per day upon sigma day into S. This is my standard deviation, this is my what you call x minus x bar is 0. So, x minus x bar upon sigma, this is my z, which gives me d s per day is equal to z into sigma day into S. We can therefore write this expression as P is equal to probability that ds per day is greater than ds star per day, which is my value at risk. This is my value at risk. ds per day is greater than ds star, which is value at risk. Putting these two values, we get P z sigma per day into S greater than z star sigma day into S. This simplifies to P, small p is equal to probability of z being greater than z star. So, this point corresponds to z star, this point corresponds to z star, and such that, and how do we determine z star? You see, try to understand. The point P, probability P is given to us, this is the confidence level. Given P, we can find z star from the normal distribution table, such that P z greater than z star is equal to P. So, z star can be found from the normal distribution, it will correspond to this point, and therefore, z star, knowing z star, we can calculate value at risk. How? Z value at risk is equal to z star sigma day into S. this z confidence is nothing but z star sigma day into S. So, and if you want a t day value at risk, you multiply by root t. So, this whole expression gives me the t day value at risk for at a confidence level which corresponds to z confidence. Right. So, do we now just a bit of explanation about the root t rule which I just mentioned in a few minutes ago. You see, again we come back to this using this per day parameters mu per day and s per day, we can write ds over t days, ds over t days as mu per day into s into dt as sigma per day into s into z into root dt, where dt is now measured in days. Please note this, because we are using mu in days. So, we have to use dt also in days, it has to be consistency, and that gives me that the standard deviation of ds over t days is equal to sigma day into s into root dt, which clearly shows that my standard deviation is scaling in terms of the square root of time, whereas the expected value of s is scaling or ds is scaling in terms along or with time with t. This is proportional to t in a sense, and this is proportional to root t. That is why we had that situation where we could ignore this particular quantity, the first factor, and we could simply model the change in stock price over a very small period of time by this second factor alone. Let us do an example. Consider a position consisting of a $0.1 million investment in an asset A. Assume that the annual volatility of the asset returns is 30%. There are 252 trading days. What is the 5-day 99% value at risk for this portfolio? Amount of investment is 0.1 million US dollars, sigma is given as 0.30, that is 30%, trading days are 252. The z value corresponding to 99% confidence level is 2.33. This can be obtained from the normal distribution table. T is equal to 5 days. Therefore, the value at risk is given by 2.33 into this S into 0.30. 0.30 divided by root 252 gives me 0.30 divided by root 252 gives me the daily volatility. So, that is where this root 252 comes. 0.30 upon root 252 is the daily volatility, root 5 because we are working out the value at risk over 5 days, and if you simplify this expression you arrive at this quantity $9846 over 5. This is the value at risk over 5 days. Now, a straightforward extension to a portfolio comprising of two assets, variance of a pair of assets x and y is given by this expression. Please note there is one important point here, otherwise the formula is quite straightforward. It is very common, we use it invariably in portfolio analysis. The important point is this left hand side variance is in terms of money units. So, it will be money unit squared, this S is in money units, sigma is in percentage. On the right hand side, please note this, left hand side sigma is in money units, and the right hand side S is in money units, sigma is in fractions, not in percentage divided by 100, this is also in money units, this is in percentage divided by 100, and rho is of course dimensionless. So, S is in money, this is also in money, sigma x is in percentage divided by 100, sigma y is in percentage divided by 100. So, this procedure is quite straightforward. If I illustrate it with an example, consider a position consisting of $0.1 million in asset A and 0.1 million investment in asset B. Assume that the daily volatilities of both the assets are 1% and that the coefficient of correlation between returns is 0.3. What is the 5-day 99% value at risk of this portfolio? 5-day 99%. Now, in this case S A is equal to S B is equal to 0.1 million, sigma B is equal to 1%, that is equal to 0.01. So, the variance of the portfolio daily change is given by this expression which we had on the previous slide. If you put the respective values and you take the square root of the left hand side, we get sigma A plus B. This is in money terms now, in US dollars, that is 1612.45. This is the daily change of the portfolio, daily standard deviation of the portfolio consisting of both the assets A and B. Therefore, the standard deviation of a 5-day change in price is multiplied by root 5, and the z value corresponding to a 99% confidence is 2.33 minus 2.33, but we ignore the minus sign when we talk about value at risk, and therefore, the 5-day 99% value at risk works out to 2.33 into 3.3605, that is 8401. From where do we get 3605? Well, we get it from 1612 into root 5. This is equal to 3605. Right, we will continue after the break. Thank you.